General relativity predicted that the universe should have a beginning. Up to 1970, my main research interest was in the Big Bang singularity of cosmology, rather than the singularities or black holes that Penrose had shown would occur in collapsing stars. My work on black holes began with the eureka moment, a few days after the birth of my daughter, Lucy. While getting into bed, I realized that I could apply to black holes the causal structure theory I had developed for singularity theorems. In particular, the area of the horizon, the boundary of the black hole, would always increase. When two black holes collide and merge, the area of the final black hole is greater than the sum of the areas of the original holes. This suggested that the area of a black hole was like what is called the entropy in thermodynamics. It would be a measure of how many states a black hole could have on the inside for the same appearance on the outside. But the area couldn't actually be the entropy, because as everyone thought they knew, black holes were completely black and couldn't be in equilibrium with thermal radiation. There was a golden age in which we solved most of the major problems in black hole theory. This was before there was any observational evidence for black holes. In fact, we were so successful with the classical general theory of relativity that I was at a bit of a loose end in 1973 after the publication with George Ellis of our book, The Large-Scale Structure of Spacetime. My work with Penrose had shown that general relativity broke down at singularities. So the obvious next step would be to combine general relativity, the theory of the very large, with quantum theory, the theory of the very small. I had no background in quantum theory, and the singularity problem seemed too difficult for a frontal assault at that time. So as a warm-up exercise, I considered how particles and fields governed by quantum theory would behave near a black hole. In particular, I wondered, can one have atoms in which the nucleus is a tiny primordial black hole formed in the early universe? To answer this, I studied how quantum fields or particles would scatter off a black hole. I was expecting that part of an incident wave would be absorbed and the remainder scattered. But to my great surprise, I found there seemed to be emission from the black hole itself. At first, I thought this must be a mistake in my calculation. But what persuaded me that it was real was that the emission was exactly what was required to identify the area of the horizon with the entropy of a black hole. It is summed up in this simple formula, which expresses the entropy in terms of the area of the horizon. and the three fundamental constants of nature, c. the speed of light, g. Newton's constant of gravitation, and h bar, Planck's constant. I am proud to have discovered it. Later work uncovered the deep reason for this formula. General relativity can be combined with quantum theory in an elegant manner if one replaces ordinary time by imaginary time. This is called the Euclidean approach because it makes time become a fourth direction of space. The Euclidean space-time is smooth and contains no singularity at which the equations of physics could not be defined. It solved the fundamental problem that the singularity theorems of Penrose and myself had raised, that predictability would break down because of the singularity. The radiation from a black hole will carry away energy, so the black hole will lose mass and shrink. Eventually, it seems the black hole will evaporate completely and disappear. This raised a problem that struck at the heart of physics. My calculation showed that the radiation was exactly thermal and random, as it has to be, if the area of the horizon is to be the entropy of the black hole. So how could the radiation left over carry all the information about what made the black hole? But if information is lost, this is incompatible with quantum mechanics. This paradox had been argued for 30 years, without much progress, which is what often happens in research. But if you get stuck, it's no good getting furious. You just have to keep thinking about the problem while working on something else. Eventually, I found what I think is its resolution. Information is not lost in black holes, but it is not returned in a useful way. It is like burning an encyclopedia. Information is not lost, but it is very hard to read. In fact, Kip Thorne and I had a bet with John Preskill on the information paradox. I gave John a baseball encyclopedia. Maybe I should have just given him the ashes. The fact that I used to think that information was destroyed in black holes was my biggest blunder. Well, at least it was my biggest blunder in science. During the 1970s, I had been working mainly on black holes, but my interest in cosmology was renewed by the suggestions that the early universe had gone through a period of inflationary expansion, in which its size grew at an ever-increasing rate, like the way prices go up in the shops. In early 1982, I wrote a preprint proposing that the seeds for structures in our universe could be created by quantum effects during inflation. This was basically the same mechanism as radiation from a black hole horizon, except that this time it came from the cosmological horizon. I had used Euclidean methods earlier with Gary Gibbons to work out the temperature of de Sitter space. We held an field workshop in Cambridge that summer, attended by all the major players in the field. At this meeting, we established most of our present picture of inflation, including the all-important density fluctuations, which give rise to galaxy formation, and so to our existence. Several people contributed to the final answer. This was 10 years before fluctuations in the microwave sky were discovered by the Kobe satellite in 1993, so theory was way ahead of experiment. Cosmology became a precision science another 10 years later, in 2003, with the first results from the WMAP satellite. WMAP produced a wonderful map of the temperature of the cosmic microwave sky, a snapshot of the universe at about 1/100th of its present age. The irregularities you see are predicted by inflation, and they mean that some regions of the universe had a slightly higher density than others. The gravitational attraction of the extra density slows the expansion of that region, and can eventually cause it to collapse, to form galaxies and stars. So look carefully at the map of the microwave sky. It is a blueprint for all the structure in the universe. Planck will test our theories in earnest, and may even detect the imprint of gravitational waves predicted by inflation. This would be quantum gravity written across the sky. The original scenario for inflation was that the universe began with a Big Bang singularity. As the universe expanded, it was supposed somehow to get into an inflationary state, but I thought this was unsatisfactory. Unless one knew what came out of the initial singularity, one could not calculate how the universe would develop. Cosmology would not have any predictive power. What was needed was a space-time without singularity, like in the Euclidean version of a black hole.